Hi guys, welcome back to the channel, and in this video I'll be discussing this cool problem called make subsequence, and this was from today's cook-off round, and this was a very cool problem and it was a div1A problem. So yeah, in case you weren't able to solve it, you can watch this video and get to know how you can solve it. So yeah, in the question you have an array of length n, and yeah, this is n. So you want to divide this array into sub arrays. So what you'll do is let's say you divide it here and you divide it into 4 parts, let's say. So this will be a one segment, this will be a one segment, this will be another one, and this will be another one. So in the question they've told you that when you partition this array, after your partitioning, the max of all these segments should be equal. And what is the max? The max is the minimum element that is not present in any array. Let's say I give you an array and this is the array, and let's say it contains 0, 1, 2, 4 and 5. So what is the minimum element, minimum positive element, or let's say minimum non-negative element that is not present in this array? So this is obviously 3, right? 3 is not present in this array, so 3 is the max of this array. So similarly, what you want is you want to partition this array in such a way that after your partitioning, each subarray has, let's say, a max. Let's say the first one has max x1, the second one has max x2, the third one has max x3, and the fourth one has max x4. So you want all of them to be equal to x, right? And you want to tell the number of ways in which you can partition this array such that this condition holds, right? So a very quick observation, it was not a very quick observation to be honest, but yeah, this is one observation. First of all, when you partition, let's consider the max of this whole array to be m. Max of whole array equals to, let me just write it, and I'm using a mouse, so please don't mind my handwriting. Max of whole array is, let's say, m, right? So what I did was, like, when I was solving this question, I tried to prove that the answer that after my partitioning, the value of this x should be equal to m. Like, this was an intuition that I had, and then I went on to prove this, and then I did the question. So I'll first of all prove that whenever you partition this array and you get this value of x, which is the max of all the which is the max of all the segments that you divide the array into, is equal to m. So I'll prove that. So let's consider two cases and we'll find contradictions for both of them. Let's say x is greater than m. So if you consider this case, you say that x is greater than m. So what you want is you want all of these segments to have a max equal to x, and x is greater than m, right? But when you found out the max of this whole array, you knew that m is the smallest element, smallest non-negative element that is not present in the whole array, right? So in order to get this x to be greater than m, all of these subsegments, all of these segments should contain the values from 0 to m minus 1, right? 0 to x minus 1. And since it is already greater than m, since x is already greater than m, so you want all the values from 0 to m to be present, right? But when we found the max of this whole array, we knew that the max is m, so m is the smallest element that is not present in the whole array. So what we know is that m is not present, right? And if we want x to be greater than m, we want each of these segments to contain the values from 0 to m. But since m is not present only, then you definitely cannot construct that, right? So yeah, this case is contradicted. You cannot have x greater than m. Now let's consider the case x is less than m, and let's try to contradict this as well. So what you'll have is, let's say you divide your how should I put it? Like, you divide your array again into segments, and you want the max of all of them to be, you want them all to be less than m, right? So right, yeah. So if x is less than m, then you know that for all of these segments, let's consider these segments like this. This is one segment, this is one segment, this is one segment, and this is one segment. So if x is less than m, then you know that in this segment you have only the value 0 to x minus 1. Similarly in this one as well, and similarly in this one, and similarly in this one, right? And this is the whole array. Let's say this is the whole array. So what happens is that you are saying that this part contains the value 0 to x minus 1. This part contains the value 0 to x minus 1. This one also, and this one also, right? So what you can see is that all of them don't contain x, right? Now none of them contains x. If you want the MEX of all of these segments to be equal to x, then you know that for sure that none of them contains x, right? But when we were finding the max of this whole array, we knew that the max is m, which clearly states that all the values from 0 to m minus 1 are present. And since x is less than m, so we know that x will definitely be present in this array, right? So this case is again contradicted. Like I'll quickly go over it again. This case wants you to have this the condition should be such that when you divide this whole array into segments, all of these segments should contain the values from 0 to x minus 1, but none of them should contain the value x, right? So if none of the segments contain x, that clearly means that x is not present in the array, right? But when you were finding the MEX of this whole array, you knew that the MEX is m, and m is greater than x, so that clearly means that x is present in the array, right? But for this condition to hold, you want that x should not be present in the array, right? So this case is clearly contradicted, like one of them is saying that x is present and the other is saying that x is not present, so they both are contradicting each other, right? So this case cannot occur. X is less than m, and as I told you, x cannot be greater than m because we know that m is the smallest value that is not present in the array, and in order to have x to be greater than m as the MEX of the segments that you will divide the array into, then obviously m should be present, right? Then only will you get an MEX higher than m, right? And m is not present in the array because m is the MEX of the array, right? So now what we know is that whenever we divide our array into segments, the max of all of them should be equal to m. And what is m? M is the MEX of this whole array, right? So this is one observation, and like this was a quick proof for that. Like you considered both of these cases, that x is greater than m and x is less than m, and then you disproved both of them. Like you showed that both of them are contradicting, right? So now what we have in the question left is, the question reduces to dividing this whole array into segments, contiguous segments. Obviously they're not subsequences. The question says subsequences, but you want to divide this array into sub-arrays, right? And let's say these are the these are the segments. So now what you want is this MEX of this segment should be equal to m, the MEX of this segment should be equal to m, the MEX of this segment should be equal to m, and again the MEX of this segment should be equal to m, right? Now what this means is that this segment should contain the values from 0 to m minus 1. It should definitely contain them, only then can the MEX be equal to m, right? Similarly, this should contain 0 to m minus 1. The values from 0 to m minus 1 can repeat, and obviously the values that are greater than m, they can also repeat, like they can also be present, but these values should definitely be present, right? From 0 to m minus 1, and similarly here also from 0 to m minus 1. Like these values are, these values should be present. The other values can be present, and m is definitely not present because m is the MEX of this whole array, right? So yeah, this is the condition, and let me bring up another slide, right? So let's see how can you do this. Like I used the dynamic programming solution for this. I use dynamic programming with sets, and you can use you would be knowing about sets if you already know about standard template library or the Java collection framework. So yeah, now let's see. Now this is your whole array, and let's say I divide this array into segments like these, right? So what you know is that this contains 0 to m minus 1. This contains 0 to m minus 1. Similarly, this one contains 0 to m minus 1. And similarly, this one contains 0 to m minus 1. Right? All of these segments should contain these values. They should definitely contain them. Right? So let's see, let's consider this, that, this is your array. and you are present at this index and you are starting your segment at this index, right? Now let's see what are the possible what are the possible endings for this segment, right? So if you start your segment from here, you should definitely go up till you encounter all of these 0 to m-1 values, right? And then you can put this closing point, but you can extend it further also, and then you can also put a closing point, because then also again the mex will still remain m. Why? Because m is not present in the array, and all the other values that are greater than m don't matter, and all the values that are less than m will only repeat themselves, right? So if you start a segment from, let's say, here, you can only end it at this point if all the values from 0 to m-1 are covered here, and thereafter you can close it anywhere. You can close it anywhere till the whole ending of the array, right? So this is one, this is another observation in this question. Then what you can do is, like, let's define a dp of I. Now what is dp of I? Dp of I clearly simply means that, what are the number of ways that I can start my segment here, right? This is simply that I'm starting my segment here. What are the number of possible ways that I can end it and form the sequence thereafter, right? So dp of I clearly means that number of ways to start my segment here, right? This is dp of I. Now let's just define dp of I, right? So as I told you that you can only end your segment when you encounter all of these 0 to m-1 values, right? So let's say the first point that you encounter this, the first point at which you have encountered all the 0 to m-1 values are I plus k, right? So you can end your segment here, and that is one possible way, right? And now what you can do is, now you can say that I have ended my segment here, so now you give me the number of ways of starting my another segment here, right? The at the very next index. Or what you can do is, instead of ending your segment here, you can end it at the very next index, and then you can say that I'm ending my segment here, and this is one way. And then you tell me the number of ways that you can start your segment after this point, right? And these both will get clear, they both will clearly get multiplied, because if you're ending your segment here, then you are wanting the number of ways that you can construct another segment from the very next index, then you will obviously multiply with them, right? Because these are independent ways and these are independent ways, right? So what your dp of I looks like is, you will have, obviously you will do a +1. Now when will you do a +1? You will only do a +1 in when you can end this segment. In case you're not able to end this segment only, then obviously you are, that clearly means that you are not able to come up with all the 0 to m-1 values, and that means you cannot end this segment. So in that case, the dp of I will be 0, equals to 0 if you're not able to end it, right? This is your dp of I. dp of I equals to 0 if you're not able to end the segment that you start at the ith index. And what other case you can have? If you're able to end it at the I plus kth index, then you will have 1 plus, because you've ended it there, right? Then you will simply have dp of I plus k plus 1, because you're starting your index, you're starting your next segment at I plus k plus 1, right? Plus dp of I plus k plus 2 plus dp of I plus k plus 3 plus so on up to dp of n minus 1, right? This is your dp, this is how your dp will look. So I'll formally define it again on the next slide. So dp of I equals to 0 if the segment that you start at I cannot be ended. And it equals to, another case is dp of I equals to 1 plus dp of I plus k plus 1 plus dp of I plus k plus 2 and plus so on up to dp of n minus 1. Right, so this is your dp, and I'm hoping like this should be clear to you because I've explained this problem in a very detailed manner. So yeah, this is how your dp looks, but how will you find this k? Like if you are standing at the ith index, how will you find the smallest I plus kth index? I mean, how will you find the smallest k such that I plus kth is the index at which you encounter all these 0 to m minus 1 values? Right. So how do you go about doing this? Now, I've used a set for this and I'll quickly explain to you how am I doing this. So I'll bring up another slide here. So now what we're doing is how to find k. How to find this k, right? So what you can do is you can start from the back, right? And you can have a set, right? And this set will store pairs. And what these pairs will look like is, a pair is simply this. Last occurrence okay, give me a minute, I'll write it more clearly. So here your pair is, pair equals to last occurrence of x comma x, right? This is your pair. Now what does this last occurrence mean? Like if you are at this index, so your last occurrence of x, I mean your x could have occurred here, your x could have also occurred here, so, but your last occurrence will be here, right? Because this is the last time that you encountered x, right? So this is how your pairs will look like. So initially, initially you haven't encountered any x, so what you'll do is you'll mark their last occurrence as infinity, right? And when you mark this as infinity, in the set you will store from all the 0 to m minus 1. I mean, you will store all the pairs for 0 to m minus 1, and initially all of them will have something like this, comma x. These will be your pairs in the set. And obviously, all of these pairs will be distinct because first of all, this index can never be same for two pairs because obviously the x will be different as you're considering all the values from 0 to m minus 1. So yeah, this is how you will store your pairs in the set. And now what you do is whenever let's say you're at this index, I mean, let's consider this array. Let's say you're at this index. So what you'll do is, let's say this value is y. Now you will go into your set and you will say that, get me the value of x. I mean, you can obviously store a vector in which you will store the actual, you can store a vector in which you will store the values that are there in the set for correspondingly x. And then, you can extract that specific pair and see what is the value, I mean, what is the last occurrence of y. And you can simply update it. Like, let's say the last occurrence of y was z, and now the last occurrence of y will be I, right? If you're at the ith index. So your pair would have looked something like this, zy. And now you will update it to I, y. You will remove this pair and you will insert this pair, right? And this is like acting like a priority queue. Now what you will do is, if you want to check that, what is the maximum, I mean, what is the minimum that I need to travel so that I, encounter all of these 0 to m minus 1, you go into your set and, you consider the very last index, because the very last index will contain the farthest element from 0 to m minus 1. And you need to consider that element, right? Because that is the element that will make you go towards it. Like all those elements, all the elements before that will be already considered, but you need to go to this last element, right? In order to encounter all these 0 to m minus 1 values. So what you'll do is you'll go to that index I mean, you'll go to the last index of the set and you will see the value present there. And that will be the specific index till which you need to go if you want to, start your segment here. Right, and if it is infinity, then definitely it means that you cannot end your segment if you start at I. Right, so this is, I mean, about the explanations part for finding how to find k. But as you can see that your DP of I looks something like this: DP of I plus k plus 1 and so on up to DP of n. I mean, it is not depending on n minus 1. It is not depending on one single value. It is depending on many values, right? And what you can observe is that, if you are at DP of I plus k plus 1, then all the other values, they will get added, right? So you can maintain a suffix sum. I mean, this is a very cool trick in DP that, you can store your suffix sums. So what your suffix sum will store is that if you are at this index, your suffix sum will store DP of I plus DP of I plus 1 to so on up to DP of I n minus 1. I mean, you will add all of these values of DP and you will store the suffix sum at this index I, right? So you'll also have to store this, and I'll quickly show you my code for this one. And I know this has been, a very long explanation, so bear with me. Right, so what I'm doing is I'm taking the input n, then I'm putting it into an array. I mean, I've constructed an array and I'm putting the values that I'm getting into that array, and then I'm maintaining an occurrence array. Okay, there is some issue. Let me copy this code into CLAN and explain it to you there. Okay, this code was already here. So what I'm doing is I've taken the input n, then I've constructed an array and I'm storing the values in this array. Then I've constructed an occurrence array, which can be used to find the mex. So what I've done is I've stored these values, and to calculate the MEX, I've simply traversed in the occurrence array from 0 to n plus 1 and seen if the occurrence of this element is 0, then definitely this element does not come in this whole array. So this has to be the MEX, right? And what I'm doing is this is the next positions vector is simply telling me that if I start my index, I mean if I start my segment at I, when will I end it, right? So initially I have marked them as I, that if you start at I, you will end at I. This is simply to consider the case when your MEX is equal to 0, because if your MEX is equal to 0 and if you start at a particular index, you can definitely end at that same index only, right? And then if my MEX is not equal to 0, then I'm doing what I've told you. So what I'm doing is I've constructed a set of pairs, and then I've marked all of these values as infinity first of all, and then I'm inserting it into my set. And as I told you, I'm starting to iterate from the back of the array. And yeah, if this value is less than m, then only I will update my value in the set. And what I'll do is I'll first extract the current index of this element in the set, and I'll erase that particular pair. Then what I'll do is I'll update the index, I'll update the current index, and I'll also update it into my index array, into my index vector, and then I'll insert it into the set. Right, and as I told you, I'll extract the very last value of the set, and this is how you can extract the very last value of the set. And if it is equal to infinity, that simply means that you cannot encounter all the 0 to m minus 1 values still here. And in that case, your next position is -1, signifying that if you start here, you cannot end your segment anywhere. Right, and similarly, if if that is not equal to infinity, then you mark it as p. Now what I'm doing is I've constructed my dp vector and I've constructed my suffix sum for dp. And similarly, I start iterating from backwards. And if the next position is not equal to -1, if the next position is equal to -1, it simply means that if you start your segment at I, you cannot end it anywhere, right? And in that case, I won't do anything. But if it is not equal to -1, then I'll go to that index p. And first of all, I'll consider this one way that you can divide your array till here. And then what I'll do is, if that p is less than n minus 1, then I'll add my suffix sum into this. Right, as I told you that we have to add it into a suffix sum. We have to add the suffix sum. Right. So this is simply like taking the mod, and then I'm updating my suffix sum. And at the end, I'm simply printing the DP of 0, because if you start at index 0, I mean, your first starting point should be the 0th index, right? So yeah, that is it for this solution video. And this has been a very long video. And in case you appreciate my efforts for this, please do consider subscribing to the channel. And in case you found this video helpful, please like and share it. So yeah.